This is part B of this first analysis problem using finite element procedure. I mistakenly ended the video in the first part of the video, so I'm going to just give you an overview of how to actually implement how to solve this problem on the MATLAB. I've already done the bulk of the explanation to solve this problem in my PowerPoint. So this will just be a summary. So here, what you see a live. I've written a live script which I'm going to use to solve this problem, and I'm also using a manual function which I wrote to help me compute my local stiffness matrix for each element. So this is our problem which we have defined in the first part of the video. So the problem has 6 nodes, 12 degrees of freedom, 11 elements, and we see the arrow direction denoted by the red arrow on each element. So the first thing we do, we determine the local stiffness matrix for all the 11 elements. So, and we do that with the help of the manual function, with the help of the function which I define as a GSM here. So the function takes 4 input parameters: the angle of each element, the length, the Young modulus, and the cross-sectional area. So before running this code, I've defined E as my Young modulus. I'm working in units of Newton for force and for length millimeter. So the Young modulus is 205 kilopascal, so that's why this is defined as 205 times 10 to the 3 Newton per millimeter square. The area is given by this. The area given in the question is actually 20.7 times 10 minus 4 meter square, but because I'm working in millimeter, so I converted this to millimeter square. So that's why this is multiplied by 10 to the power 6. So our theta for this element 1 is 0 degree. I've already explained this in my previous video, so I refer you to my previous video to understand why theta 1, the theta for this element is 0. The L1 is given, that's the length of the element, given as 2 meters, 1000 mm. So if I should enter this variable which I defined in my K1, my local stiffness matrix, which I'm defining as my K1, if I enter theta, the length, the Young modulus, and area, K1 is when I run this code, K1 will be calculated and stored in the MATLAB memory. Same thing for K2, same thing for K3, same thing for K4. You should refer to my video, the first part of my video for explanation on this input parameter if you don't understand this. So K5 is also calculated. So the local stiffness matrix is calculated for all the elements till the 11th element. So this is the global stiffness matrix for the 11th element. So after we have computed all the local stiffness matrix, the next thing we need to do, we need to define elast stiffness for our support degree of freedom. In the question, as I have already explained, at node 2 and node 4 we have support. So it means that and node 1 and node 4 has degree of freedom 1, 2, 7, 8. So it means this we have 4 support degree of freedom 1, 2, 7, 8, and at that 4 support degree of freedom we have to add infinity, we have to add elast stiffness to the diagonal elements of the global stiffness matrix at 1,1 of the global stiffness matrix, at 2,2 of the local stiffness matrix, at 7,7 and 8,8, because at 1, 2, 7, and 8 we have support degree of freedom. So that's why I define K1R, K2R, K7R, K8R as infinity. I'll add these values to the diagonal element of the global stiffness matrix after I've assembled the global stiffness matrix with the local stiffness matrix. So once we have defined this large stiffness, next thing you need to do, you need to define a base matrix. I normally start to assemble my global stiffness matrix. I define a base matrix, and that base matrix is a zero matrix. And the size of this zero matrix is 12 by 12. Why is it 12 by 12? Because our problem has 12 degrees of freedom. 12 degrees of freedom, as you can see in the question. So that's why you have 0, 12. This 0 is a MATLAB inbuilt function that generates a matrix of any size you want. You enter the input parameter in the bracket here. This 12 tells MATLAB I want a 12 by 12 matrix. So this is a 0, 12 by 12 matrix, my base matrix. So to this base matrix, we need to add our local stiffness matrix to this matrix. For the element 1, I'm adding K1 to the base matrix. So this is done using this MATLAB line of code. I explained this MATLAB line of code in the first part of this video, so I urge you to go back to that video. So this matrix, this line of code will add K1 at this point. Remember, our local stiffness matrix is a 4 by 4 matrix. So this is actually where K1 is added in the global stiffness matrix. This is the K1 matrix, what I highlighted here. Once I run this code, this matrix gets the local stiffness matrix get added to the base matrix. So you do this for K2 too. K2 is located between degree of freedom 3 and 6. As in 3 to 6. You can see 3 column 6. That is 3, 4, 5, 6. Element 2 is located between degree of freedom 3, 4, 5, 6. So this is the it means at this position 3, 4, 5, 6. K2 is added at this position. So this is the K2 matrix which is added in this position of the global stiffness matrix. You do this for all the matrices till you get to the 11th matrix. Let me explain this. The local stiffness matrix for the assembly of the local stiffness matrix of the 8th element. For the 8th element, we have 3 column 4, 7 column 8. So for this, it means I've explained this in my previous video, but I will try and explain it again. For this, it means at 3 along the road 3, 4 at degree of freedom along the road at 3, 4, 3, 4, 7 and 8, 7 and 8, and along the column at 3, 4, 7 and 8, add K8. So K8 added at that position. So this is actually the K8 component. 3, 4. This is K8 is a 4. The local state matrix is a 4 by 4 matrix. That's 16 components, 16 values. So this is one part of it. 3, 4, 3, 4, 3, 4, 7, 8. This is another part of it. 7, 8, 7, 8. This is another part of it. 7, 8, 7, 8, 7, 8, 3, 4. So these are the components of the K8 matrix added to the base matrix. So we do this for all the components till we get to the last local stiffness matrix, which is K11. So after we have assembled all the local stiffness matrix for all the elements, what we need to do, we need to add the last stiffness at the along diagonal of the assembled local stiffness matrix. This is our final assembled local stiffness matrix from the element. But now we need to add this support stiffness as a modification to the global stiffness matrix. So because at node 1, node 2, and node 7 and 8 we have support, we need to add elastiveness, which I'm defining as infinity in this lesson, to 1, 1, 1, 2, 2, no, 1, 1, 1, 1, not that, 1, 1, okay, 1, 1, 2, 2, 7, 7, and 8, 8. Because that is the position where we have support degree of freedom in our question, as you can see here. This is the model. At node 1, we have support, and degree of freedom there is 1 and 2. At node 4, we have support, and degree of freedom is 7 and 8. So that's why we add elastic stiffness at this position in the global stiffness matrix. So you see, I'm adding infinity. This MATLAB line of code, I defined K1 out earlier as infinity in my earlier as infinity. So I'm adding infinity to 1, 1. So you see the infinity value here. This code adds infinity value at 2, 2. This code here adds infinity value at 7, 7. That's at this point. This code here adds infinity value at 8, 8. So these are the four modifications to the global stiffness matrix. So this is the final modified global stiffness matrix with the support modification. So it's given by this. So once we have assembled our modified global stiffness matrix, what we need to do, we need to define our force vector. That is the vector of all the forces at each node. And the size of the force vector is the size of is the number of degree of freedom. In this question, we have 12 degree of freedom. So it means that our force vector will be a 12 by 1 matrix. So that's why we have a 12 by 1 matrix defined here. And in this question at node 2, we have 0.5 kilonewton force. At node 5, we have 2 kilonewton force. At node 6, we have 1 kilonewton force. We have 3 forces. So we have to define this in our force vector. And this 0.5, my force unit is in Newton. So that's why you are seeing 500 here at position 4, because the degree of freedom, the direction of this force is at degree of freedom 4, and it is pointing downward. That's why it is minus 500. 0.5 times 1000 is 500, and it's pointing downward, minus 500 Newton. At node 5, it is also pointing downward, minus 2000 Newton, in degree of freedom 10. So at position 10 of this vector, I add minus 2000. At position 12, I also add minus 1000 Newton. That is at node 6, at position 12. Because 1 kilonewton is acting in the 12th degree of freedom. So that's why we have minus 1000 here. So now we have defined. So at other position, we don't have any force there. So that's why you see 0 at other point. 0 at degree of freedom 1, 2, 3. At 4, it is minus 500. At 5, 0. 6, 7, 8, 9, 0. At 10, minus 2000. At 11, 0. At 12, minus 1000. So once we have defined this vector, the next thing we need to do, we need to compute our displacement vector. And it's simple, you just multiply the inverse of the modified stiffness matrix, global stiffness matrix, times the force vector. So once you run your MATLAB code, once you click on run here, this matrix is calculated. As you can see, at node 1 and node 2, we have 0 there because that's our support degree of freedom. Also at 7, 8, we have 0 because that's our support degree of freedom. At other point, we have displacement quantity 3 to 6, also from 9 to 12. 9 to 12. So this is our displacement quantity at the 12th degree of degree of freedom from 1 to 12. So what we can do with this vector here, we can extract what can we extract here? We can extract the displacement vector for each element. For element 1, I've explained this in my previous video. For element 1 is located between node 1, between the degree of freedom 1 to 4. Like here, this element 1 here, and element 1 is between node 1 and node 2. And the degree of freedom at that point is 1, 2, 3, 4. I'm taking my numbering as 1, 2, 3, 4 because the arrow is pointing from node 1. If the arrow is pointing from node 2, the numbering will be 3, 4, 1, 2. But it is 1, 2, 3, 4 because the arrow is pointing from node 1. So 1, 2, 3, 4, I'm going to extract. So this MATLAB line of code extract 1, 2, 3, 4 from this DS matrix. DS 1 column 4. 1 column 4 means 1, 2, 3, 4. So once I run this code, I'm assigning this vector to DS1. So this DS1 is my displacement vector for element 1. DS2 is my displacement vector for element 2. It's located between degree of freedom 3 to 6. 3, 4, 5, 6. So this is it. You do this for all the 11th elements. For all the 11 elements. So DS11 is my displacement vector for the 11th element. And the 11th element, if you check, is located between this 11th element here. Is located between node 2 and node 6. And node 2 and node 6, we have degree of freedom 3, 4, degree of freedom 3, 4, 11, and 12. And because the arrow is pointing from node 2 to 6, we take the numbering of the degree of freedom from node 2. That is, so the degree of freedom will be 3, 4, 11, 12. If the arrow was pointing from 6 to 2, in the other direction, the numbering will be 11, 12, 3, 4. This is very important when you're extracting your displacement vector. So the numbering for this 11th element will be 3, 4, 11, 12. That's why in this MATLAB code we have 3, 4, 3 column 4, comma 11 column 12. This one means 1 column 1. That's 1 column. You must specify this on MATLAB. So this is how you define. This is how you extract the 11th element from the displacement vector matrix, the global displacement vector matrix, a 12 by 1 matrix. So this is the displacement vector for the 11th element. This is at node 3, this is at node 4, this is at node 11, this is at node 12. So once we have done this, actually there is a purpose for doing this. The purpose is actually to calculate the axial force in the x and y direction for each of the elements. And in the first part of my video, I explained this. I told you that the axial force is given by the local stiffness matrix multiplied by the displacement vector of each element. And the local stiffness matrix is a 4 by 4 matrix, the displacement vector is a 4 by 1 matrix. So we can multiply both of them together to get the axial force in the x and y direction at both nodes of the element. I've explained this in my previous video. K1 is a 4 by 4 matrix. DS1 is the displacement vector for element 1. So we multiply them together, we get this. So this 5.4634 times 10 power 3 Newton is the force in the x direction at node 1. There's any force at node 2. At degree of freedom 1, this force rather, at degree of freedom 2, the force is 0. at node 1. These two are the forces at node 1, while these two are the forces at node 2, 3 and 4. At node 3, we have the force pointing to the left, you will see better explanation to this in the first part of my video in the PowerPoint presentation. So you do this for P1, P2, P3, P4, P5, P6 to P11 to compute the area force in the x and y direction for each element. The area force vector for each element is a 4x1 matrix, as you have seen. So once you do this, you can interpret this into this. Element 1, 5.46 kilonewton compression force. Element 2, 0.94 kilonewton compression force. Element 3, 5.54 kilonewton tension force. Element 4, 1.06 kilonewton tension force. Element 5 is a zero member, no force. Element 6 is a tension member, compression member rather. Element 4 is a compression member, 0.70 kilonewton. Interpret the force vector in a graphical format like this. Element 7 is a compression member, 0.47 kilonewton. Element 8 is a tension member. We have the x and y component. So if the x and y component is in this direction, that means the resultant will point outward. Also here to point outward. So this is a tension member. You can find this resultant by finding the square root of the sum of the square, how I put it, the square root of this number and the square root of this number, the square of this number and the square of this number, you add them together and you find the square root. So that is the resultant. So this is a tension member. This, because of the direction, the compression member, the resultant is in the direction shown. This is a tension member, this is a compression member. So this is how it is defined. This is how you analyze plane truss problem using the finite element procedure in MATLAB. And it should be, as I said in the beginning of my video, in the first part, the finite element procedure is very similar to the stiffness matrix method of analysis. The stiffness matrix method of analysis is another method of structural analysis in the field of civil engineering. So the finite element procedure is actually the same. It's very similar to the stiffness matrix method. So this is how we solve truss problem using the finite element procedure by penalty approach. And this penalty approach, I actually use the last stiffness, which I define as infinity. In my next video, I'll use the normal approach for penalty approach, where the last stiffness is defined by the largest element in the global stiffness matrix multiplied by 10,000. So we are going to use that approach to solve this same problem in my next video. Before I will close, I would like to say, if you want to develop your skill on MATLAB, I recommend a MATLAB course on Coursera website. I'm going to drop the link under this video. The name of the course is MATLAB for Scientists and Engineers. I think it's taught by a US instructor in a university in US. It's actually very good. You can learn the basic of using MATLAB as an advanced calculator, which is what I'm doing here. So I recommend that course for you to improve your skill on MATLAB, basic skill on MATLAB. Also, I'm going to upload a link, a downloadable link for this live script under this video, under the description section of this video. So check it, download it, and you can go through each of my MATLAB line of code to understand how each MATLAB line works. Also, if you want to download the original version of MATLAB, you can, as a student, you have access to the original version of MATLAB. All you simply need to do is to register with your student mail on their website, and you'll be given access to download the original version of MATLAB. Also for Ansys, the same thing. On their website, you can register with your student mail and you are granted full access to the Ansys Finite Element software program. So I've come to the end of my video session now. Thank you so much for watching my video, and I hope it has been impactful. You can drop any question in the comment section, and I will create time to answer your question. I always find time to answer question in the comment section. If any part of this learning session, if you don't understand any part of this learning session, you can ask your question from the comment section. I'm going to respond to the question there. So thank you so much for watching my video. Have a nice day.